Question 2, on a Tuesday for review day. State what is meant by work done. So if we think about work as being the dot product of force and displacement, we kind of mentioned that when we said, oh, well, work is a scalar. So work done is force times displacement, but only the component of force acting in the direction of displacement contributes to the work done. So you could say the component of force acting in the direction of displacement times displacement is work done. I wouldn't let an equation stand as a statement. It's a nice mathematical statement, but you want to kind of use words to answer that. So put it in your own words, best you can. Now we have a beach ball, and it's released from a balcony at the top of a tall building. The ball falls vertically from rest and reaches a constant terminal velocity. The gravitational potential energy of the ball decreases by 60 joules as it falls from the balcony to the ground. The ball hits the ground with speed 16 meters per second and kinetic energy 23 joules. Show that the mass of the ball is 0.18 kilograms. I think the easiest way to do that is to just use this information here, because we know that kinetic energy is equal to 1/2 mass times velocity squared, and they give us the speed, the velocity, and we're asked to solve for the mass, and they give us the energy. So we got sort of 2 out of 3 unknowns. We'll plug them in and solve it. Let's solve for mass, and so let's rewrite this as twice the kinetic energy, right? Multiply both sides by 2, get rid of that, and then divide each side by the velocity squared. So that should be the mass there. Plug it in over here on this side. 2 times 23. When Michael Jordan first came out of retirement, they had already retired his number 23 from the Chicago Bulls, and so he wore his brother's number 45. That's actually why he chose the number 23 when he first started playing, because his brother was 45 and he wanted to be like half of that. But you know, it's an odd number, so he just chose like the next one up. So we're doubling 23. That's 46. Okay, not Michael Jordan in the 4-5. 16 squared. Also, 23 pairs of chromosomes, right? That's another. Talking about biology earlier. 23 pairs of chromosomes we've got. All right, so 46 over 16 squared. Why do I feel like that's not gonna, oh yeah, 16 squared is a big number. So 46 divided by, so you do indeed get a calculated value of 0.1796875, which is about 0.18 kilos. I don't think there's another way to solve that. 60 joules. Yeah, you don't know the height of the building. If you did, you could use the potential energy, because remember that's mgh, so you can still like solve for m. We can say, well, it's on Earth, so we know g, but we don't know the height of the building. So really, I think that's the only path to the solution, is to use kinetic energy. Calculate the height of the building by the ground. Well, there you go. And I think that the reason why this is calculation number 2 is because now that we, sort of know the mass, we should be able to use potential energy equals mgh. Before it was like, well, can we use this to solve for mass? We'd realize, oh, that's an unknown and the height is an unknown. But because this is, step 2 now, remember they told us 60 joules is the potential energy that's sort of decreased over that. So that's a given value. We now know that the mass is about 0.18, it's like 0.179 and change. we can assume this is happening here on Earth, 9.81 newtons per kilogram, and then solve for the height like this. So really, I could have done what I sort of did over there, which is solve it in variable form first. So the potential energy over the weight, mg, or mg is the weight. And again, this just comes from that same definition of work. Like, state what is meant by work done. Well, work is energy. The force that you overcome when you lift something is its weight, mg, and the height, that you lifted is its displacement. So this comes from the work done lifting something, the work that gravity does when it sort of drops something. So 60 joules over 0.18 times 9.81. $33.97. That's about 34 meters. Get building height of 34 meters. Now it wants us to determine the average resistive force acting on the ball as it falls from the balcony to the ground. Okay. Average resistive force. So the average resistive force, again, like we start with work is force times displacement. So we need an equation that includes the thing we're solving for, resistive force. Okay, how can work sort of relate to this? I mean, you might say, well, can I solve it F equals ma? Do I have enough information to like figure out its acceleration? Maybe I could solve for the force like that. And so sometimes you have to sort of scour the equations that you have in mind and say, well, what type of problem really is this? I just did some stuff with energy, right? One calculation leads to the next. The work is the energy. Work is energy. If I have an energy budget of this thing lost 60 joules of potential energy, but only 23 joules is kinetic energy by the time it's sort of hitting the ground, I'm missing some energy, right? Like there's an energy budget that is not balanced here. And you may have in mind this important idea of the law of conservation of mass energy. Mass energy is neither created nor destroyed. The initial energy equals the final energy. So here we are accounting for sort of the lost energy, that energy that was lost due to heat. As a beach ball crashes through air, there's a resistive force slowing it up. That's why it reaches terminal velocity, doesn't accelerate all the way to the ground. So the first step is to calculate the work done by friction, by the air. And it's just the difference, 60 minus 23. So we're assuming all these energy losses is the work done by a resistive force. And so it's just an average over the entire motion. So I have a 37 joule energy budget. That's the work done by friction. I want to know what the force was. If it acted over it, all 34 meters it fell, right? This is why I calculated the height. Remember, the same equation for potential energy due to gravity is just the work is force times distance. When the distance is vertical, we call it height. When the force is the force due to gravity, we call it weight, equal to mg. Work is energy. So those are one and the same. So we're just going to take 37 over 34. 1.09. 1.09. State and explain the variation, if any, in the magnitude of the acceleration of the ball in v during the time interval when the ball is moving downwards before it reaches terminal velocity. Okay, so the variation in the magnitude of the acceleration of the ball. Here's what a velocity time graph looks like for something that reaches terminal velocity, okay? It picks up speed, and depending on like how much area it has, the density of the air, there are equations that sort of govern the drag force. They have to do with the density of the air, the cross-sectional area of the thing falling. And we can kind of look at this and say, okay, the magnitude of the acceleration in v, the time the ball's moving downwards before it reaches terminal velocity. So like its terminal velocity is here. So we're saying what's happening to the acceleration during this part of its motion, right? Here it flat lines, it reaches a top sort of final speed, that's the terminal velocity. The acceleration initially is greatest because there's just weight, the weight of the beach ball sort of acting down. Because the drag force is proportional to velocity, when it first is dropped at speed of 0, there is no drag force. And so it accelerates the most under sort of that force. As it starts to pick up speed, the drag force becomes more and more pronounced. What's happening at terminal velocity is this situation. The drag force equals the weight. That's why it flatlines. And so what's happening to the magnitude of the acceleration, we really have to consider the net force. We have to sort of anchor our thoughts into Newton's second law. If we say, well, we can deduce what's happening with the net force here, okay, because we know that the drag force, that resistive force that we just calculated, it's an average, right? It started out small and it got bigger. So we just sort of averaged it over the entire time. What's happening to the acceleration? What's happening to the slope here? The slope starts out steep and then it gets shallower, and it gets shallower until eventually it's 0. So we can just sort of use that to describe the magnitude of the acceleration. It's decreasing. Okay, state and explain. So you'd want to kind of put that into your own words. The magnitude of the acceleration is decreasing. Because the net force is getting smaller, or is also decreasing, as the drag force cancels out. And this is where it's like, this is my language, right? So the way I would kind of word it is I would say, as the drag force cancels out more and more of the weight. Like I said, like the drag force isn't canceling out any weight at first. Then it cancels out a little bit of it, and a little bit more still, eventually all of it, right? Eventually you can crash into so much air so fast that the force that's pushing up on you will equal how much force you're feeling right now as you sit in your chair, right? You can crash through air so fast that you could have a force, acting on you like that. But you have to jump out of an airplane to do it. It's like not a lot of people can just run, reach sort of terminal velocity. Well, I guess bicycles. All right, so the net force is also decreasing as the drag force cancels out more of the weight vector. So once again, you start with all weight, and then as you pick up velocity, because the drag force is proportional to velocity, the more drag force, until eventually they're equal, and that's terminal velocity. The magnitude of acceleration is decreasing because the net force is also decreasing as the drag force cancels out more of the weight vector. And you can say, as it picks up speed or throughout its motion, something like that. I think pretty well answers it. That would be the end of that. Second question. All right. There you go.